And really I don't mind if you would like to move around a little bit, to look outside the windows and to jump from left to the right side of the ship. But today, because 2 nights ago, not the night before, the last night, but the 2 nights ago, we had a very nice light phenomenon, which is called Aurora. And Aurora is the light phenomenon which occurs not only on the north side of our globe, but also at the south side. And they have 2 different names. It's the same phenomenon, but appears on 2 different locations. And in the North Pole, the place close to the North Pole, the Arctic Circle, it's called Northern Lights or Aurora Borealis, because of boreal area. And on the South Antarctic Circle, it's called Southern Lights or Aurora Australis, because of Australia. Australia in the south, because we at the south we are quite limited with the land area, and you want to be on the land to have good aurora observations. And you can, if you are familiar with our globe and continent, if you look at the south hemisphere, we are missing a little bit of the land area to stay on the ground.
Well, ladies and gentlemen, I hope you enjoy the whale spotting. It was minke whales, and at least we had 2 or 3 of them. We're now starting to go a little bit starboard and slowly continue and hopefully see more wildlife up there.
So,
also make an announcement if I see anything in there. Thank you.
Minke whales on the starboard side. But coming back to the Southern Lights and Aurora Australis, and why Australis? Because Hobart and Tasmania, which is part of the Australia, is the best place on the land to see them, because otherwise we need to go to Antarctica, which is quite difficult. And here are a few examples of aurora. You can have beautiful examples when you are sailing, especially in the Arctic Sea, when you can have beautiful mast and the aurora at the skies, or when you are at the land, and especially when you are able to be close to the land, when you can have also a little bit of a perspective and a little bit something at the background for a photography. It gives you a little bit more of aurora experience. And here another one, and you can see actually it's the same area, same photo, but probably a minute after. So you can see also the aurora is moving. It's not just one band of light, but it's constantly moving. Like last 2 nights ago, you could see it's a little bit like a waves moving left and right across the skies. And aurora. What does it mean, aurora? Or anybody is familiar with the name aurora?
Sun going up?
No, that's aurora. Yes, aurora in Latin means morning light.
Yeah.
But also, if you will think about Roman mythology, there was a goddess, which was the Aurora. Name her was Aurora, and actually the first mention of, let's say, Northern Lights we had in the history was made by Pythias. It was a Greek explorer, and he spotted it probably somewhere in the 4th century before Christ. So that was the first written observation of Northern Lights we have. But the proper name of Aurora came up in 1619 by Galileo Galilei. But unfortunately, he thought he saw aurora, but he only saw the morning light. So he was somewhere traveling in Europe, and he got up early, he saw beautiful reddish sky, but unfortunately it wasn't the proper aurora, the proper Northern Lights. It was only a sunlight reflection from the atmosphere very early in the morning. So unfortunately for him, he missed that, because you need to be very high in latitude to see that light phenomenon. And the first scientific understanding of aurora came from very early 1600s. There was an Englishman, his name was William Gilbert. He was living between 1544 to 1610, and he put the first thesis about this light phenomenon. And also William Gilbert was the first person who invented a device, let's say, which is called terrella, and terrella means in Latin little earth. And here you can see, it's not a photo from 1600s, there was no photography at that time, but 300 years later, this Norwegian gentleman, which is Christian Olaf Bernhard Birkeland, in early 1900s, so 300 years after William Gilbert, he little bit developed this little terrella. And now the little terrella, it's not anymore a little earth, it grew up a little bit. And with this vacuum chamber, you can see this big case, and inside it's a brass ball. And the brass ball is, magnetized. And the brass ball is in a vacuum tank. And there are two, unfortunately, you cannot see it, the quality of the photo is not the best, but you can see beams of light which are coming from the right side of the vacuum tank and on the left side. And these stream, the light of stream, these are projected electrons and protons. And by the electricity on this brass ball, on the north pole of the magnetized brass ball, you can see illumination, concentration of these protons and electrons which are enlightened at this north part, at the north latitudes of this brass ball. And this was the first time that the scientists, they could understand how aurora doesn't work. So we came up with this idea to understand this light phenomenon very late in our time. So now we know, because we have a sophisticated devices, scientific precision devices, so we know exactly that the aurora occurs only in a thermosphere. So here we have the Earth at the bottom, troposphere, stratosphere, mesosphere, thermosphere and exosphere. These are the spheres that we have which are surrounding our planet. And there is a big layer of the thermosphere which extends from 90 kilometers to up to 600 kilometers above our planet's surface. And there is a little part of it, at the bottom part of it, which is called ionosphere. And ionosphere because we have ions there. And ions of protons, electrons, neutrons, very small particles of gases, because our atmosphere is mostly built up with neutron, oxygen, and nitrogen, with oxygen, nitrogen and helium. These are the three most abundant atoms in the air, but they are in the molecules, they are in connected, the atoms there, they are connected. For example, when we are here, we are breathing oxygen mixed together with nitrogen. So they are together, they are bonded. But when we will fly to the thermosphere, and they are starting to collide infrequently, and they started to be separate. So there is no more carbon dioxide or nitrogen dioxide. The atoms, they are floating in this part of space as singular atoms. And then with these we are coming into how to cook our aurora. What do we actually need to prepare it? So if you think about making a meal, you need to put some ingredients. So with Aurora we need to have the same principles. So what do we need for Aurora? Anybody has an idea? Sun. We need to have a star. We need to have a star which produces a huge amount of energy. And for us, in our solar system, we have a few planets which are circling about big star. And our star is the sun. So what else do we need other than a sun? Planet. And we need to have a planet with magnetic field. Because the planets without magnetic field, they are not able to interact. And the third thing which we need is an interaction between a sun and the planet with magnetic field. So here is the photo. It's a little drawing, a little circle, and that circle is our Earth core. So this is the visualization of Earth magnetism. Earth is, if you put the Earth into the sections, we have a crust which we are now on, and beneath the crust we have two cores. One is solid and the other one is liquid, and the elements in the core are ferromagnetic, which can be magnetized. And because we have two different cores, which one is solid and the other one is liquid, and the liquid one is moving all the time around the solid one, it's create Coriolis effect and a magnetism. And it works very similar to the magnet bar. So you can see these lines which are coming from, and also this is quite interesting what I'm going to say, because everybody thinks that the North Pole is at the north and the South Pole is at the south. But it's not like that, because our planet, the South Pole of the magnetism is at the north, and the North Pole of the magnetic field is at the south. So it's a little bit different. And why? Because these lines are electromagnetic lines of particles moving. So you can see they are moving from, and all of them, they are always the plus and minus, which are always moving from plus to minus. And we always think that in the indication for the north it's plus and the south is a minus, same as a battery. So here we have a magnet bar, and you can see the magnet bar at the north is south, and at the south is north. And you can see that all of this line, they are moving from north to south. So it's very similar system. So here it's a very nice visualization from NASA. They make a very nice little animations about Aurora to better understand all these processes which are on our planet. So here is the visualization of Earth magnetic field, and it looks like a donut. And you can see these little lines which are a little bit like spirals. This is actually the Coriolis effect we have on our planet magnetic field. And they are, you can see that they are going from the south but the north, and then they are going all around to the top side of our planet. And also you can see that these lines are mostly concentrated at the poles, at the extremities. And this is also very interesting, because Aurora, because of that effect, because of this Coriolis effect, Aurora only can occur, it's visible in these places where we have the highest concentration of these lines. And why? A little bit later. And now with the planet with magnetic field, we are coming into the sun. So this is our second ingredient, powerful star, a sun, and sun also has magnetic field. But the magnetic field of the sun is a little bit more complex, a little bit more complicated, because you can see all of these lines coming up and they are a little bit all over the place. And why? Because there is no solid core in the sun. The sun is a fluid. From the central point to the outside, it's all fluid. And that's why you have multiple of these lines coming out and into the sun. And what is interesting, the sun also has a north and a south pole, but the north and the south pole of the sun is switching every 11 years. And 11 years, it's a sun cycle. Every 11 years we have another cycle, and now we are probably, now we are in the cycle 25 of our sun, and the cycle started in 2021, the cycle 25. So we are getting up with the activity of the sun, but also about it a little bit later. So sun, powerful star, and now sun, we are talking about activity of the sun and how we measure the activity of the sun. The activity of the sun we measure by the sunspots, these little black holes. The more of these black holes we have, the more active our sun is, because you need to think about these sunspots as hotspots, and it's little bit like a tunnel between the inside part of the sun to outside. It's like a little bit of the tunnel connection between the surface and the central point of the sun. And why it's important? Because surface of the sun is way cooler than the inside part of the planet and the corona, which is around the sun, which is quite interesting. But also about a little bit later I will have a photo of it. So if you will think about sun, it's a huge ball, and if you compare the size of Earth to the sunspot, it's quite interesting to compare it. So more sunspots, the more energy we have, so the more heat from the core of the sun can go out. We have a better aurora, but also it influences the climate on our planet. And Claudio will give you a little bit information about climate changes, but now I will just go into the 400 years of sunspot observation. So all of these lines, and you can already see the cycle pattern, this little sinusoid which is going up and down, up and down, up and down. It's 11-year cycle of the sun. So we have every 11 years we have a peak of solar activity. So the more these sunspots we have on our planet, but between 1650 to 1700 our sun was having a little bit long nap for around 50-75 years. And what happened during that Maunder minimum around at this time, it happened that between 1600 to 1700, closer to the 1700, we had a little ice age. And if you are from London, and if you know a little bit about history and about festival which happened in London, there was a very, very famous time in the 1670s, 1680s in London, when there was a festival during the winter on frozen Thames, because River Thames in London was completely frozen. So that's quite interesting. So here we have sun. So this is a beautiful photo of the sun. It's dark, but what is the most important for us is this part, this colorful part. Because if you think about these numbers are temperatures in Kelvin, and the core of the sun is around 15 million kelvins, so it's a little bit below 15 million Celsius degrees. Surface of the planet, I already told you, it's much cooler. And corona, which is this plasma which surrounds the sun, it's again much warmer. And why? Because these hotspots, these sunspots, the more sunspots we have, corona also is getting more in warmth. They're getting much more energy, which is shooting out of the core of this 15 million, almost 15 million Celsius degrees temperature. By these tunnels to the surface, the energy can be released to the outer space. So again, sun, and we have these beautiful loops. We have a corona, which is the plasma which is moving outside, and the corona, these shooting particles from the core, we call as a solar wind. And you may think that we have a day and night, so sometimes during the night sun is sleeping, so we don't have a light anymore, and like a bulb, yes, on and off, on and off. But not. Sun is on all the time for 24 hours a day, and sun all the time is producing, is shooting out from the core and from the surface with the corona, the solar wind. So sun is all the time producing the solar wind, and this solar wind is traveling with speed, with supersonic speed, from 250 kilometers per second to sometimes even to 800 kilometers per second. So that's a fast moving particles, and the solar wind is a stream of charged protons, electrons and plasma, which is traveling with this speed with 800 kilometers per second to the outer space, and is reaching all the planets from Mars, Venus, Jupiter, Saturn, even to Pluto. So it's moving all the time, and you can see these jumping loops, and these jumping loops are coronal mass ejections, CME, the scientists they call it, and they are a little bit like rubber bands. If you have rubber bands and if you will stretch it too much, it will snap. And when one of these coronal loops, which are moving from these sunspots, when one of these coronal loop will break off, will break up, then will be a coronal mass ejection, which means that there will be more protons and more neutrons, more of this plasma substance will be released from the sun, because you need to think that sun also has a magnetic field and everything is moving back. It's quite powerful. The magnetic field of the sun is much bigger object, so the gravity and the magnetic field is much stronger. So you need to imagine how much power, how much energy needs to be for these protons and neutrons to be shot out with the speed of 800 kilometers per second. And this is how it looks like. So this is the little animation, and you will see the process of when our planet is here. Here is the Earth, Sun is there. So here is the little visualization of the coronal mass ejection. So when the Sun is the most active, these bands of these loops are breaking off, and then you can see these little lines. This is a solar wind full of particles and protons and all the stuff which is moving, which is interfering with our planet. So here we have our planet, you have a regular activity of the sun, and in the back you can see more lines. And they are slowly starting to speed up, and you have a little bit like this. And you can here see already there is something interesting going on the right side of the planet. So here is our planet magnetic field, these yellow and blue lines. But it's a little bit, it's not anymore a donut. It's moving a little bit away from the sun. So how does it work? So I already said that the sun activity is constant and dynamic. It changes a little bit during the day, during the days and years. And you can see that there are a few different things that are presented. We have a sunlight, we have a X-ray emission, we have a radio noise emission, energetic particles, magnetic storm, and the solar wind. So from the top, and also we have here a timeline, which starts from 0 and it goes from 8 minutes, 15 minutes, 1 day, 4 days, and 10 days. So this we are getting into how we can predict things on our planet, because sunlight, it takes around 8 minutes for a sunlight to travel from the sun to get to our planet's surface. It's 8 minutes. So this light we have right now was 8 minutes ago on the sun, produced from the sun 8 minutes ago. And now we are coming into the more interesting part, which is the flares and the solar wind. And if you'll see here, solar wind has 4 days and it's constant. Sometimes it's a little bit faster because we have flares, we have these coronal mass ejections which are traveling a little bit faster, and the 4 days. So it takes 4 days for a solar wind to be produced from sun, and then that the sun will hit our magnetic field in 4 days. So the difference between 4 days and 8 minutes gives us the prediction of aurora of 3 days, because sunlight travels with 8 minutes, so the coronal loops that we can observe will see much faster than the magnetic storm will arrive. Do you understand? Perfect. I found explaining aurora the most difficult topic and I hope I'm doing pretty good. And now we are coming back. So this is the interaction, yes? So we have our planet with magnetic field. We have our sun, which is pool of energy, and we have an interaction between these two objects. So here we are coming back again to the magnetic field of our planet. We have our planet, magnetic field, and you can see already that it's something going on with our magnetic field. It's not anymore a perfect donut, but you can see these magnetic field lines which are coming from north to south. They are a little bit of disturbed. Here we have a sun, and because of this powerful event of projecting very high supersonic speed solar wind, these bands started to be extended, elongated, they started to be pushed. And there was, on the animation which I showed you before, there was this shield, there was that bow shock. And the bow shock, it's a protective, it's a boundary which protects us from the solar wind. Because if we wouldn't have a magnetic field on our planet, most likely we would not exist. Anything would not exist on our planet, any form of life, because solar wind is so powerful. So with the magnetic field, it creates a little bit of the protection of our planet, and disturbance, the high disturbance of these magnetic field lines creates aurora. So you can see that these protons and electrons, they are getting, some of them they are passing through the magnetic field. These magnetic lines, they are concentrated in these little points when the magnetic field is the weakest. And then the cusps, the protons, electrons and other stuff is getting into. So this is our magnetic field. This is the tail side, right side, the night side of our planet. Sun is here. So it's getting inside. these lines. And there is something you need to think about Aurora, about this light phenomenon as a charging battery. So if you imagine our planet as a battery with two poles, plus and minus, it's by the solar wind, which is flow of electricity, our planet is getting charged. And what is happening when you overcharge the battery? Probably it will explode. So, with this extremely high solar activity, when there is a coronal loop which broke down, there is a coronal mass ejection, there is a big disturbance on our planet. There is a lot of electricity, energy getting into our planet. So, what is happening? The sun side, I will reverse a little bit. I hope I can stop it. No, unfortunately not. I cannot make a stops. But you can see that these bands are slowly breaking off. So they are charging, so the planet and the magnetic field is charging. These loops are moving to the other side, to the tail side. And then they are getting more denser and denser. So they are squeezed and squeezed and squeezed. And at some point, there is... they are going to be reconnected from the tail side. And these reconnection release the energy. So we don't want that the Earth will be blown up. So there is a massive energy release by the reconnection of these magnetic lines on the tail side. And when it's reconnected, energy is released, and we have illumination of Aurora on both circles, of both around Arctic and Antarctic circle. And you can see these blue lines, these are our magnetic lines, and you can see that the most concentration of them we have the 66 to 75 degree latitude, north and south. And then we have beautiful spectacle of lights. So the protons, as I said already, protons and neutrons, they also can be charged. Electricity is happening in our magnetosphere, and oxygen, nitrogen and helium are getting excited. They are excited by the electricity, and when the energy is released, they are from the excitement form, they are starting to release energy and electricity, and the photons are started to be illuminated. And the photons, the different atoms, they will produce different colors, also at a different altitude, and also different electromagnetic spectrum, because if we think about color, about prism, we have colors of the sunlight from ultraviolet to infrared. So from very purple violet to very red color. And color has also electromagnetic spectrum. The light has an electromagnetic spectrum, and we present electromagnetic spectrum of light in units, and the units are called nanometers. And with different nanometers we have different color of light. So for example, the most common is green, and the green color is illuminated in the aurora at the altitude of 120 to 200 kilometers above the surface in the ionosphere, and it emits electromagnetic spectrum of 557 nanometers. And the green is the most color because at this part of our ionosphere there is a high concentration of oxygen. So oxygen is getting excited. There is no aurora visible, but when there is energy release, the photons, they started to be illuminated, and then oxygen will start to be enlightened in a green color. The red color is the next in common, this transition between between green to red, and we have these yellow, blue, beautiful colors to the red color above 200 kilometers in altitude, and then also oxygen will be enlightened, illuminated, but concentration of the oxygen is much lower. And the last color that we can see is a blue color, very difficult to find, and it's very dim blue color, and it's at the lowest part of the ionosphere, because it's below 120 kilometers, and this is not oxygen involved but the nitrogen, because we are getting into the stage of our atmospheric air when we have a little bit over 70% of nitrogen in atmospheric air, and then nitrogen is going to produce this beautiful blue violet light. So you need to have a lot of sun activity and disturbance of the magnetic field of our planet to see these blue colors. So what are the results of Aurora, this disturbance of the magnetic field? It's beautiful, but it can be quite destructive, because it works like an EMP, which is the electromagnetic pulse. So the electromagnetic pulse with contact with electricity, it doesn't work really well, so sometimes we have a disturbance. We have, for example, GPS signal scintillation, or we have damage to spacecraft electronics, because these guys, GPS signals and spacecrafts in the orbit, they are the most endangered because they are the closest to that ionosphere and the closest exposed to this solar wind. Sometimes we have a problem with aviation. Sometimes instruments are getting a little bit weird readings, but also pipelines and the regular cables, regular electricity we have in our towns can be disrupted. So for example, in 1989 there was a huge geomagnetic storm, and you could see Aurora even in Texas. So it's very quite south. So it was possible to see Aurora in Texas, and at that time in 1989 almost whole province of Quebec influenced a blackout. So there was no electricity because of the magnetic storm. So what are the units that we can read when we are predicting Aurora? That we are predicting the geomagnetic storm. We are not predicting Aurora, but we are predicting the disturbance in a magnetic field. So there are a few interesting things. This is the NASA Space Weather Enthusiast Dashboard, which is very, very nice website, which is organized together with NASA and NOAA. And you have a solar wind speed. The faster wind speed, it means that more disturbance we will have. We have a solar wind magnetic field, BT, BZ, very interesting things which tells us how strong it can be. Also we have this interesting KP index, and you can see that the KP index is from 0 to 9. It's a kind of scale that we can it's not predicting Aurora. So for example, if there will be KP index 9, I would say there are the most chances to see Aurora, and the lower value of KP index, the least chances to see Aurora, but still there is a chance, because it all depends on the disturbance of the magnetic field, and the KP index also will tell you if there will be disturbance of the magnetic field, how low in latitudes you will be able to see Aurora. So here we have KP index from 2003. It was at the time when we had the peak of the solar activity in 2003. So you can see October 30 and October 31st, we had a crazy time of the solar activity and the geomagnetism disturbance with the KP index up to 9. And with this scale, we have a KP index here on the left and geomagnetic latitude that the geomagnetism can be disturbed. So with KP 0, you still may see aurora, but the best observation of aurora you'll have at 66.5 and higher to 75. Then, for example, we go to the middle part of the scale, which is KP4, and the auroral activity is active. You can see that the geomagnetic latitude is going lower. It's moving lower into closer to the equator, which is 58.3, and with KP index 9, you may see aurora with disturbance of the geomagnetism even below 48-degree latitude north and south. So that's why during this big storm in 1989 you could see aurora even so far south, like in Texas. And you can see also it's extreme storm, and the average frequency, you can see how rare these extreme storms are during the cycle. It's 11-year cycle, so during these 11 years the KP index 9 is only 4. So you have only 4 years in these 4 days in these 11 years that you have these huge geomagnetic storms. And this photo I was able to take in Poland. I was in the coast at the north part of Poland, around 52 latitude north, and because of the prediction of aurora, I took the chance. I took the car with my friend, we drove to the coast of Poland, and we took that photo. And coming further into, you can see this is aurora forecast, and you can see during the aurora forecast you can have this very colorful map, mostly and above north hemisphere and the south hemisphere, but for us the most interesting is the north hemisphere. So this was the aurora prediction for 2015, March 17th, and you can see these colors. So, and then these colors tells you the probability of visible aurora. The redder it gets, the better aurora observation it will be. And you can see that it's an oval, it's a donut, yeah, it's a part of this donut. And at the North Pole, during the regular aurora activity, most likely we are not going to see aurora. It's quite interesting, because do you remember these loops which were breaking and moving to the tail side, to the night side of the planet? It's coming. It's referring to these lines. Why we don't see aurora at the equator and also at the very high latitudes. So the best location for us to see aurora is between 65 to 75 degree latitude north. Why not below 65 degree latitude south? Because we want to also, coming back, aurora, northern lights can be 24 hours a day. So it's not only during the night. Aurora is happening, the disturbance of the magnetic field is happening 24 hours a day. But the sunlight is too